Sorry. Good morning, ladies and gentlemen. Thank you for joining us today for this webinar on the interesting topic Satellite Radar for Disaster Response. This event is brought to you by the NTU Institute of Advanced Studies and the School of Physical and Mathematical Sciences Graduate Students Club. My name is Shivam and I'll be your host for this webinar. As part of the webinar housekeeping rules, please turn off your webcams. All attendees' mics have been muted to prevent any accidental disturbance to the presentation. If you would like to ask a question during the Q&A session, you can use the raise hand feature at the bottom of your Zoom screen. The speaker for today's webinar is Dr. Sang-Ho Yoon, a geophysicist and radar scientist at the NASA Jet Propulsion Laboratory. Dr. Yoon received his PhD in geophysics and MS in electrical engineering from Stanford University. Prior to joining NASA Jet Propulsion Laboratory, he was a National Research Council postdoc at the US Geological Survey. As the disaster response lead of several projects, he and his team have supported over 70 major disaster events globally. He received the 2018 NASA Exceptional Public Achievement Medal and the 2014 NASA Exceptional Early Career Medal for innovative use of satellite synthetic aperture radar data in support of rapid post-disaster response. He is currently the principal investigator for 3 NASA projects to develop algorithms and systems for global rapid damage and flood mapping, as well as human activity monitoring for the COVID-19 global pandemic response. Without further ado, let's welcome Dr. Yoon. Dr. Yoon, please.
Morning, and thank you all for joining the seminar today. I hope all of you are safe and healthy. This work was done with many people at JPL, Caltech, and through the wonderful partnership with the Earth Observatory of Singapore at NTU. And I also would like to acknowledge support from NASA Disasters Program, as well as NASA Rapid Response and Novel Research in Earth Science Program. In this presentation, I included key contributors' photos, so you may see some familiar happy faces along the way. Now, I want you to imagine that you are in charge of a disaster management office in Jakarta, Indonesia. You didn't sleep well last night because of the sound of thunder and pouring rain. The next morning, you wake up to hear that there's massive flash floods happening in Jakarta because there was 40 centimeters of rainfall overnight. By the way, this actually happened on the New Year's Day this year. Then what would you do? You tell your team members to check all the available satellite images to get an idea of what the extent of the floods, right? A couple of hours later, 10:30 a.m., your team brings the first satellite image. And this image was acquired from MODIS, mounted on Terra satellite. And you're frustrated. And 3 hours later, 1:30 p.m., your team brings the second satellite image acquired from MODIS sensor, mounted on an Aqua satellite. And you feel more frustrated. Then comes the synthetic aperture radar, or SAR. I don't know how many of you are familiar with SAR. If not, you're probably familiar with radar. So I wrote synthetic aperture radar, but let me read it as high resolution imaging radar. So the technique utilizes the Doppler shift of the radar signal and some brilliant processing methods to achieve a few orders of magnitude higher resolution. So it's a high resolution imaging radar. And radar penetrates clouds and can image both day and night. So 4.5 hours later, so on this European radar satellite, SAR satellite, Sentinel-1 acquired this data. and then we'll produce this image. And notice that there is no cloud in this image. There's some features in the sea, probably boats, and you see the clear distinction between the sea and land, and you see small features on land. So again, the atmosphere is crystal clear to radar 24/7. And then we compare this. This is during the flood image. Compare this with prevent image, prevent SAR image acquired in December 21st. And if I go back and forth, you can see the difference, right? Before, after, before, after. So we use this image to produce this flood map. So this map was generated at EOS, so the background is the optical image base map from Google Earth, and the foreground, the right light blue color pixels represent where floods were. And this flood map was delivered to the AHA Center, the ASEAN Humanitarian Assistance Center, and they use this to assess how many people were affected by this event. And by the way, on the same day, December 21st, if you look at the optical image, it looks like this. It's very cloudy. Clouds are always the problem with optical sensors. And in fact, if you look at, this is April 2015, over that month, average cloudiness of the Earth in April of 2015 looks like this. It's a mosaic of the aqua satellite imagery. And turned out that 70% of the Earth is obscured by clouds. So that's your chance to see clear sky with optical imagery. And of course, optical imagery requires sunlight. But radar sensors carry its own light source. It's a radar transmitter. So you don't have to rely on the sunlight. So that's why it can image day and night. Then you may ask, okay, that's great. SAR system sounds great, but how many are there? And then how many, more importantly, how long do you have to wait until the radar satellites can acquire data? And this is the plot shows the overpass latency of SAR satellites. It's a statistically calculated quantity. So x-axis is the time and y-axis is the number of days latency that you have to wait until you see the first SAR satellites flying over you. And this color-coded, there are like tens of SAR satellites, and it's getting more and more, putting them in space and operational. And it's color-coded as different frequency. So these satellites use this microwave radar, and the blue color is a short wavelength, or we call it X-band, and green color is a little longer, about 6 centimeters. This is about 3 centimeters. Orange is like 12 centimeter. Red is 24 centimeter wavelength. That's what these satellites are using for their signal. And if we combine all this, by the way, these are all civilian satellites, not, they're also military satellites. If we combine all these civilian satellites all the time, so if we consider some missions that we have reasonable access to that goes up to 10 hours, if we consider a SAR mission that has open data policy, which is Sentinel-1, that goes up to about 30 hours. But this is still very good news that we only have to wait about 30 hours until the first time we see, after an event, the satellites flying over us or wherever you are where the event happened. So with that deluge of these SAR data, about more than a decade ago, at JPL and Caltech in California, we started building this system, and we called it ARIA, or Advanced Rapid Imaging and Analysis Project. And we have been developing algorithms and systems that would automatically get notified from some event notification and discover relevant SAR data, download the data, and process and produce decision support products. And we have many partners. Now back to flood mapping. So you may have been wondered how this map was generated. Remember, you saw this flood map. So the SAR image is a two-dimensional array of complex numbers. So each element, each pixel, is composed of two parts, real parts and imaginary parts. Or you can make it amplitude and phase. So it's complex number. And we're looking at, in this case, an amplitude of pre-event, before the flooding, an amplitude image, which is basically an absolute value of SAR image. And this is amplitude of co-event, or during the flood. Now, the basic mechanism is like this. The satellite transmits the radar signal, and the radar signal hits the ground, and the signal gets scattered into all different directions because of its roughness. And then some of the signal goes back to satellite, and the satellite records the information, and it produces image. Right, it's like a magic, right? When the surface, rough surface, is replaced or covered with flooded water, it becomes smooth. So what happens is that when the radar signal hits the surface water, it reflects away. Most of its energy gets reflected away from the satellite rather than going back. So this part, the corresponding pixel, becomes darker, as you can see here. However, there's another mechanism. If there are vertical structures like a building facade or vegetation sticking out of the water surface, then the radar signal gets bounced once and twice and goes right back to satellite, call it double bounce. And that promotes the corresponding pixels to become brighter, like, for example, in this part. So we mark both pixels that became darker and brighter to produce this flood map. So that's when we compare before and after SAR scenes. And we take further steps to produce better flood map, because the before image does not necessarily represent the ideal dry state. It can be, there can be another rainy day, but not flooded, or some anomalous condition than just a regular dry day. So what we do is we collect multiple number of SAR scenes before the flooding, and then construct the statistics out of it, and compare with that statistics. So here's a SAR image again. This is complex number, and then we, after applying radiometric and thermal calibration, we produce backscattering coefficients in dB, decibel. And then we normalize it to by dividing the standard deviation of the prevent scenes after subtracting the mean to make it a unitless and expressed in terms of how many sigmas away from the expected value. And then we produce a probability. This is conditional probability of flooding. So the question is this pixel flooded or not? So this is basically the answer. Conditional probability given the observation, z-score. We cooked z-score, and then that's our observation. And this is very difficult to solve. To come up with this quantity, it is very difficult. However, the Bayes theorem gives us a very nice way of turning the table around. If we can estimate the flip side, the inverse of the conditional probability, meaning probability of observation given that pixel is flooded, and probability of observation given that pixel is not flooded. And we can produce this from the distribution of flooded and non-flooded area, and then just plug it in to calculate our desired conditional probability. That's how we make it, and we call that flood proxy map 2. 2 doesn't mean much to you, but it's just internally what we call FPM2. By the way, all the flood map we produce, we call it flood proxy map because it's a proxy to flood. It's not really assessed on the ground, observed on the ground. It's a remotely sensed database product. So flood proxy map. So this is advanced flood proxy map algorithm. And we take further step using deep learning technique. Since flooding has some spatial correlation, we take advantage of that information. Also, flooding is highly time varying. So we want to combine those two. And the idea is that we combine CNN, convolutional neural network, and RNN, recurrent neural network, which is CNN is mostly for spatial analysis, RNN is for forecasting, more temporal analysis. And we're combining the two to make it more agile, adaptive to our problem. So one example is combining the two is called PredRNN++. Here in this example, you see a person walking in the video or snapshot, sequence of snapshot. And by training these with these 3 scenes, we can predict what's going to be the next scenes and the next scenes, and then compare with the real observation. And you can see it's not perfect, but it's pretty good, promising results. And another example is precipitation nowcasting. I think it's a Doppler radar-based precipitation map because it's used a lot in nowcasting and what's going to be the next step, because this precipitation blob is changing shape over time. So it's a good application for this type of approach. In our case, now we call it FPM3, deep learning. We use, again, multiple. This is showing Lumberton, North Carolina in the United States. And there was a flooding here in this town, Lumberton area. And this is the airport runway. It's a SAR image, SAR amplitude image. And you can see, I don't know if you can see these blue boxes are the testing tile and the others are training tile. So what we did was we trained with the prevent scenes only in these training tiles, and then fed the data and asked the machine to predict the next step. And in this case, n+1 step. For information, n+2 step is flooded scene, and we produce expectation n+1 step and compare with the n+1 steps observation. And of course, the next step is to produce expectation of n+2 step and then compare with the observation, and then produce the anomaly score map to see if what you see in here, for example, in this observation, is that expected or anomalous? If it's too anomalous, we mark it as flooded. So, and then we compare that with this validation map, which was painstakingly produced at NTU. I thank you guys if you had participated in producing this map. NTU, a lot of NTU students, volunteering students, NTU interns effort. This validation map was generated from NOAA's 30-centimeter optical imagery, aerial photos. So we're using this as a golden standard, and whenever we think we improved our algorithm, we go back and compare with this validation map. Here, so deep learning results here, we see going through hundreds of iterations at the beginning, it thinks that, okay, here, negative anomaly here is close to the marked flooded area. So this is flooded area. You see this W shape, and it's correctly marked. However, it also marked like existing water body, and it also marked airport runway. But as the iteration goes on, you can see this highway runway is gone, existing water body is gone. However, the flooded urban area, it's hard to see at this level, but there are flooded urban area here. Double bounce induced signal is still there in this result. So this effort is still ongoing using this spatial temporal analysis. Also, at EOS, ALOC is also doing CNN-based flood mapping algorithm development. It's basically using one-dimensional CNN for each pixel. It's a supervised classification, whereas this one is unsupervised. So multiple efforts are going on to improve the quality of flood map. So that was flood mapping. Now we move on to the damage mapping. So going back to SAR image, remember SAR image is a complex number, so it has amplitude and phase. Now, in SAR is interferometric SAR, or SAR interferometry. What it means is that you involve two complex numbers. You involve two SAR images, and then you multiply the second SAR image pixel value after taking the complex conjugate. What happens is that amplitude gets multiplied, yes, and phase gets differenced. So we call this interferogram. This product of C1, C2 star is an interferogram. And we call this phase, argument of this complex number, interferometric phase. If you look at the interferometric phase of right place at the right moment, in this case, last year on an Independence Day of the US, there was a big earthquake in Ridgecrest, California. And we processed this Japanese JAXA's ALOS-2 data and produce this interferogram, interferometric phase. If you look at the phase, you suddenly see this beautiful picture. This is not just beautiful, this is also informative, because this color cycle, the rainbow pattern, gives us information of how much this part of the ground has displaced with respect to the location of satellite. So, for example, in this case, one color cycle represents 12 centimeters of displacement in the line of sight from satellite. So what you do is, if you want to know this amount of displacement, this part of the ground, you just have to count the number of the fringes, like 1, 2, 3, 12 centimeters times 3 is 36 centimeters here with respect to this portion of the ground. So this is very high precision measurement observed from the space. The precision can go down to like millimeter scale when the measurement is made from 800 kilometers above the ground. So it's an amazing technique. It also conveys another information. If you calculate, so from C1 and C2, which was acquired one before the earthquake, one after the earthquake, if you calculate correlation coefficients, which you call coherence, it produces some values. And this value matches where these fringe patterns become noisy. So it is an excellent metric to express the quality of the interferometric phase map, because it tells you which parts are noisier. So this part is noisier, and the fringes in this part is not very reliable, not as reliable as other parts. So it's a noise. Now we take that noise as our signal. That's the birth of damage proxy map. So we developed this algorithm to produce maps that show which buildings are damaged after major earthquake. And the first event we applied is February 2011 Christchurch earthquake. Japanese satellite acquired this data 3 days after the earthquake, and we produced this map. At that time, we didn't know what to do because there was not other independent observations to compare against. And then 4 months later, the New Zealand government first produced this damage zone map after they compile all the ground observations by 300-400 geotechnical engineers. And you can already see the spatial correlation between the two. There are some discrepancies, like here, it's green, this is red. And guess what? Another 4 months later, they updated the map. Now, combining also the observation of the ground damage. This was mostly house damage. Now you can see even closer, even higher spatial correlation between this radar-driven product and the ground observation-based map. So that was quite encouraging. And then we responded to this event, magnitude 7.8 Gorkha earthquake, or on Nepal earthquake in 2015, and we produced this map. At first, we thought these were all false positives in the mountain, but it turned out culturally they were, or for some reason they were living like in a scattered way inside this Himalayan mountain range. And there were a lot of houses here, but they were quite sparsely located. And then after comparing with NGA, National Geospatial Intelligence Agency's map, point clouds produced by looking at before and after high resolution optical imagery, we confirmed that, okay, our map carries some useful information there. So we quickly shared, and then a lot of responding agencies, NGA also used our map to guide their work priority to produce their maps. And also Digital Globe used our map to task their satellites, because there's radar scenes have wide swath, in this case like 50 kilometers, and Digital Globe's high resolution optical sensors have a narrower swath, like 12 kilometers. So if they image a wrong place, then they would have to wait for the next satellites to visit. And also on the ground, GEAR team, Geotechnical Extreme Event Reconnaissance team, they went out in the field after downloading our map onto their smartphone. Fast forward, and in 2018, 2 years ago, there was a Palu earthquake, and magnitude 7.5 earthquake caused a massive landsliding and lateral spreading and liquefaction. We produced this damage proxy map. And then, interestingly, we saw some pattern in the DPM, damage proxy map. So we decided to investigate further. This was led by Kyle Bradley at EOS. And our findings was very interesting. So it turned out at the beginning of 20th century, the Dutch colonial government constructed this modern tropical irrigation system, and the major part of the effort was to construct aqueducts, like aqueducts here. So all this damage, pattern damage extent was bounded by this aqueduct. And this aqueduct was built to improve the reliability and productivity of wet rice cultivation. The problem is, when you have a wet rice field, you maintain the rice fields wet, right? So effectively, so this is a cross section of this gentle slope. So what was puzzling was that slope was only like 1 degree or so on this alluvial fan. But because of this wet rice field cultivation, effectively you raise up the water table to the ground surface. So what happened is that this creates the liquefaction hazard already in that area. And that hazard turned into a disaster triggered by the Palu earthquake. And soon after the earthquake, we actually had a chance to visit the AHA Center in Jakarta, and they were super busy responding to the event. And they told us that their #1 question was, where is the safe place? For them to decide where to put the internally displaced people or IDP and their disaster response camps. So based on our findings, we didn't know where is safe, but we knew where it's not safe. Basically, all these the locations below the aqueduct. This is the high ground, this is low ground. Below the aqueduct is still posing this liquefaction hazard and landsliding hazard if there's any like aftershocks. So we quickly shared our manuscript with the AHA Center before this was published. So our our study had a real impact in this area and to the responding agencies. Some quotes from our customers. In the background, it shows Amatrice. It's an old town in central Italy. The Amatrice earthquake totaled some section of this village. And a team of engineers went out and then saw the ground observation really matches well with our damage proxy map. And former President Barack Obama also mentioned our product when he was hosting former Prime Minister of Italy. And then also in during Gorka earthquake, the OFDA, Office of Foreign Disaster Assistance under USAID, they use our product as well. And we also afterwards, so all that event response support were damage proxy map 1 or DPM 1. Since then, we were also lucky enough to build this partnership with EOS in Singapore and NTU Singapore, and cloned our system using Amazon Cloud, cloned our system in Singapore. So I think you should feel lucky that Singapore has no natural hazards. It's a very safe place. And we're so happy to have our clone system at EOS in Singapore. And it's not just because it's safe, but also EOS has a whole suite of wonderful scientists and wonderful working relationship with the neighboring countries. So we feel very lucky. So we take further step to test deep learning technique on damage mapping as well. It's similar to the FPM4. Was it FPM3? FPM3. Here, it's pure RNN, recurrent neural network. But the idea is similar. We use coherence map from the nearest pair and multiple coherence map and produce an expectation at the timing of after the event, after the earthquake, and then compare with the real observation and see if that's normal or abnormal. If that's anomalous, then we mark it as damage. If it's expected, then it's not damage. Performance-wise, you can see this is DPM1 or coherence loss or simple coherent change detection method. You can see there are some noises outside, but by deploying RNN method, DPM4, we suppress the noise. We basically improve the signal to noise ratio. So this is also ongoing effort, but it's ready to be submitted for publication. That was DPM4. DPM2. This is, by the way, DPM1, 2, 3, 4. 2, 3, 4 is all engaging different methods and is customized, and it has pros and cons and customized for particular applications. Let's look at DPM2. This is DPM2, and this is part of Puerto Rico. This is before Hurricane Maria hit Puerto Rico. This is after, and red polygons indicate where damaged buildings are. And this is DPM1, and by using multi-temporal SAR analysis, we produce DPM2, and you can see the different noise level. This part, by the way, I don't know if you have noticed, this part is still not detected. That's because before the event, now after the event, like trees are gone. Before the event, these houses were covered with trees. Tree canopies were obscuring the view of the radar satellite. This is ROC curve. I'll get to that point. Basically, it's a performance metric, one of the performance metric. DPM1 0.68, whereas DPM2 is 0.81. And then we, for the first time, deployed our DPM2 algorithm for real response to support January this year, Puerto Rico earthquake, magnitude 6.4. This is a small town called Guanica in southwest of Puerto Rico. And this is a DPM2 map, and quickly validate our product with using cell phone photos and street level photos acquired by Civil Air Patrol, which is expressed in this case, point clouds. Some places we produced some pixels somewhere. I don't know if this was that blob. It was not there, but later on they confirmed the damage because the street level photos, ground truth information takes time to build. This is, now we're seeing Japan. This is a DPM of landslide. That was an earthquake-induced building damage previously. This is landslide-induced building damage, in this case, DPM1. The landslide, there were like hundreds or thousands of landslides were induced by Hokkaido earthquake. And DPM1 is showing where there used to be houses, and then they're gone because of this massive landslides burying the buildings. So it's doing its job, but if your application is to map out the extent of the landslide, it's not doing well, as you can see. So we developed this new algorithm. Internally, we call it DPM3, involving also amplitude information of the SAR image, and then improved to produce landslide extent map like this. So the idea is that when you have a detection algorithm, ideally, you want to have signal distribution be like this. So pixel value distribution inside this polygon. This is signal, and pixel value distribution outside the polygon, so noise. Ideally, you want them to be completely separate so that you can easily select a threshold here and get the job done. But in reality, this is almost always not the case. And their pixel value distributions are overlapping each other, sometimes too much. But trying to separate as much as possible, that's what we did from going from DPM1 to DPM3, so that certain threshold is distinguished the two effectively. So ROC curve or receiver operating characteristic curve is commonly used in binary detector to as a metric. So basically what it does is, so here it's a signal distribution and it's a noise distribution, and whatever is, and then this is your threshold, above which you mark it as damaged, below which you mark it as not damaged. And we're comparing the true positive rate, which is marked as damage, over the true damage, and then false positive rate, which is you mark it as damage, but it's not. It's a false positive. So basically you sweep your threshold from right to left and look at how quickly your true positive ratio goes up and how quickly your false positive ratio goes up. So at the beginning, you see this goes up vertically, and at some point, you start touching the noise distribution, and this start going to the right, and basically that's what it is. What does it look like when the signals are having like much overlap versus no overlap? Like no overlap, it's basically a diagonal line. It's a useless detector. Perfect detector, on the other hand, is going to have an L shape, and the area under a curve becomes 1 in that case. For useless detector, AUC is 0.5. Okay, so now here's a metric. DPM1 is 0.68, whereas DPM3 is 0.93. So not only your eyes can see that, oh, this is better, but how much better? And this is one of the metrics that we can use. If you zoom out a little bit, and so this area was where we were looking at, you can see there are a lot of landslides indicated with this black polygons, and you can see DPM1 map, DPM2 map, DPM3 map. Really, DPM1 and 2 is suffering in much vegetated area. As you can see, it's more vegetated area. 1, 2 is suffering, but DPM3 is clearly outperforming the other two. We also tested some more sophisticated algorithm using some non-local averaging technique. Our DPM products are mostly registered to SRTMDN, which has 30-meter posting. If your purpose is to detect where landslides are and do your analysis, this is just fine. But if you want to really delineate the boundary of the landslide, we can do that because in this case, the native radar image resolution was 3 meter. So we maintain the native resolution of the radar image and then produce the DPM. So of course, it's much more time consuming, but it is possible. Speaking of time, all this algorithm development efforts and then fancier and more accurate products, they don't come for free. In fact, they're very expensive. In terms of latency, it could take 1 or 2 weeks to produce DPM 2, 3, 4. And that's often too late because in response business, if you go beyond 3 days or in 72 hours, then it becomes recovery phase, not response phase anymore. But we are solving this problem by using ARIA systems elastic computing environment and bringing it down to latency of about 18 hours so that we can still produce useful enough products for our responding agency customers. I wonder, do some of you see these two color bars almost the same in color? So this is to accommodate like products with our knowledge, statistical knowledge. 1 in 12 men in the world have this so-called color vision deficiency or partial colorblind. We also introduced this colorblind friendly color palette so that For example, in the original color palette, our damage proxy map is like this. But to colorblind, red-green colorblind, this severe signal just disappeared like this. Again, here, another example. This red just blend in with surrounding green. So we now started producing another color palette product that uses the blue color instead, which still shows up to colorblind. So that's one of the things that we recently did. We're currently doing this COVID-19 response project. And we started looking at this area in Shanghai. What you see here in the background is black and white optical imagery. And these color pixels represent the areas where the activity slowed down. So we've been seeing this damage proxy map, which is anomalously large disturbance suddenly happen after an event. We flipped that method. We use the same idea, but we're looking at the other end of the spectrum to search for places where disturbance, the regular, usually happening disturbance is gone. So the lack of activity, lack of disturbance is showing up as blue pixels. And it's not just a map, we call that slowdown proxy map. It's not just that map, but we also retrieve the temporal evolution information of each pixel. In this case, this particular pixel is a construction site. And what we can do is to calculate the coherence of all the possible pairs of this pixel. So let's say if we have like 30 scenes, this is covariance matrix where each pixel represents the coherence value of that pixel. Remember, coherence is inherent to pair. It's a pairwise quantity. So here, x-axis, y-axis, is chronologically ordered and represents time. And wherever you see I comma j, that's the coherence of that I time and j time. That's how you read. And in this case, when you see this clear boundary here, something happened. This means that coherence was low in this construction site because of the human activity, and then stopped and suddenly became high coherence, meaning the SAR images in this time period are similar to each other. And that timing was sometime between January 19 and January 25th. And remember, in China, the lockdown was placed in January 23rd. So that makes sense. And on the other side, sometime between March 31st and April 6th, there was a reopening or speeding up of human activity in that site. You can also see that the shutdown was abrupt, but reopening was more gradual compared to the shutdown. So that kind of information can be retrieved from our product. So we're covering about 120 or so major cities in the world. And that was construction sites. Another signal is coming from parking lots. This is Los Angeles International Airport in California and Burbank Shopping Mall in California. You can see a lot of these blue blobs are matching the locations of parking lots. And in this parking lot, shopping mall, you can even see the difference between non-essential business and essential business. They closed down, but they didn't. So you see the slowdown signal here, but you don't see as much in this part. So this is work in progress. We're working around the clock. And we're improving our understanding. We're improving our understanding as well as the quality of the product and making these products ready as quickly as possible. But in the meantime, NASA will release the media release. This is an image from an article I took from this morning, talking to NASA headquarters. So they're going to release these images soon, like within this week or so. And you will see more of our products coming in the near future. To summarize, the various flavors of flood map, flood proxy map, and damage proxy map are being matured at JPL in California and EOS in Singapore. And for the first time, we were able to produce FPM2 for Jakarta event and DPM2 for Puerto Rico earthquake. And for DPMs, we also added colorblind friendly palettes. And similar methods and ideas and approach is being applied to map out slowly occurring changes. This have a potential usefulness for post-disaster recovery phase monitoring, or now currently being applied to COVID-19 induced human activity level change monitoring. I put this figure here because the AHA Center used our map to estimate the needy supplies, such as like hygiene kits and mosquito nets for the disaster response. And these are photos. These photos were taken at the AHA warehouse in Malaysia before the supply was delivered, airlifted by the Royal Malaysian Air Force for delivery to Laos. And they kindly shared this photo after receiving our product. And this kind of feedback is very rewarding and gives us a profound energy. And we also appreciate brutally honest feedback from the ground, because I remember and believe what my first remote sensing teacher said during his class. And he asked, what is the most important thing in remote sensing? Can you guess? What is the most important thing in remote sensing? And the answer is, it's ground truth. Because no matter fancy stuff you produce, if it doesn't match the truth on the ground, it's not very meaningful. Thank you so much for your attention. And if you have any questions, feel free to email me here. And all the products that I covered today is available to download from these websites. Thank you.
Thank you, Dr. Yun, for the informative session. If you would like to ask any question, you can use the raise hand feature. When you are called on to ask your question, please unmute yourself and ask your question. In case you experience any difficulties, you can also send your question in chat. A couple of participants have sent their questions during the registration itself. Let's first take those questions. So there's a question from Balaji. What's the biggest challenge you faced in translating the raw data into something useful? And what are the possible solutions to this?
So that's a great question. What's the biggest challenge? I have to say it's a ground truth. Accessing the ground truth is, first of all, is difficult. And I feel like all this algorithm development, system development is something that we have control over. It's a technology. It's if there's a bug, we fix it. If it doesn't work, we try another method. But the ground truth, first of all, it's very difficult to communicate with the first responders to collect the ground observation. They're busy, and once they're done, they go back to their daily job. They're not unemployed. They have their daily job. So it sometimes takes an art to communicate, to make sure that you get their feedback. And feedback should be a useful form as well, just like our product has to be useful form to the responders. Also, the ground truth record they collect has its own uncertainty, and we have to propagate the uncertainty in a quantitative way in order to compare our product, which has its own uncertainty, but we have better understanding on that uncertainty. So that product, first accessing the product and communicating the uncertainty, how to translate their uncertainty to our uncertainty. That's a challenge. Yeah, I would say that's the biggest challenge, or one of the biggest challenges.
Before we start taking questions from the audience, we have another question. Benjamin wants to ask, would you say we have reached the pinnacle of satellite surveillance technology, or do you believe that there are certain advancements that could still be achieved owing to limitations of current designs?
Oh, yeah, that's a great question. Did we hit the ceiling? No. The answer is no. There are a lot to be more developed, technology-wise, also latency-wise. Like you saw that these satellite data, Sentinel-1 capturing the flash flood, that was very lucky case, because flash floods just happen as a matter of day and it's gone. Floods are like ghosts. In order to capture that kind of event, you really need like a daily coverage. And there are a lot of commercial satellites launching a number of CubeSats, small sats. We have yet to see if they can produce reliable enough interferometry capability or repeat pass capability. Have to follow the very precise orbit, the same orbit, and then very well controlled orbit, a tight orbit too, and a very precise orbit information. It's a matter of like centimeter level orbit location information. Also, there are radar issue, like without going to the details, there are advanced technology coming up. Like at NASA, we're building this new mission called NISAR, NASA ISRO SAR, that uses both S-band 12 centimeter or 10 centimeter, 12 centimeter, and L-band 24 centimeter wavelength dual frequency. And it's gonna have high resolution and wide swath. That's difficult because there's a trade-off, but we're overcoming that trade-off. Of course, there are other issues where we're addressing that. So technology is improving, and more satellites are going in the space. So be prepared to take advantage of all these freely accessible data in the near future. NISA mission is going to have also open data policy.
So now we'll take questions from the audience, and we see that Christopher Luvanga wants to ask a question. Hi, Christopher, can you unmute yourself and ask your question?
Hi, okay. Thank you, Dr. Sang-ho. I have just two questions. The first question is with regards to SAR as a technology itself. Is the reason for your use of SAR because it has inherently better properties than an optical image, or what is the reason for that? And then on the construction site photo that you showed just a couple of slides back, in that case, where is the ground truth, or what is the ground truth in those in that sort of analysis? And you want to see?
Yes.
Thank you.
Thank you for asking. Why SAR? First of all, SAR is not always better than optical imagery. It's difficult to interpret, right? It's complex number. It's complex to interpret, and it's not intuitive like optical imagery. It's not. I said it's high resolution, but it's not as high, nowhere near the resolution of high resolution optical imagery, which is nowadays like 50 centimeters. It's like a high res norm of satellite imagery, but SAR image, like high resolution SAR, is like 1 meter. And that's still like spotlight mode. strict map mode is like 3 meter. That's high resolution SAR resolution. But SAR has great unique capability that is conducive to rapid response because there's no clouds in the SAR image and it's an active sensor. So the satellite carries its own transmitter and receiver and transmit the radar signal down to the Earth. So you can image at any time, day and night, and it's only limited by its orbit configuration and repeat cycle and duty cycle, how much data it can acquire before it meets the downlink station. So it's all logistics and controllable, but not limited by weather condition or day-night condition. So that's why I think SAR brings very unique value to rapid response. The second question, ground truth. The China, Shanghai, is there a ground truth? No, we don't have ground truth on that construction site. It's only inferred information by looking at, okay, that discontinuity is right where the lockdown was placed. And reopening, we don't know. But the places where we can collect ground truth data, we are doing that. For example, the Burbank shopping mall I showed you, my postdoc and I are driving out every 6 days. Every 6 days, we drive out to that shopping mall, and with our cell phone, we take a video, and then we mark where the cars were parked. Also, we hired a drone flyer. We're doing this on this shopping mall because the airport is right next to it. It's the no drone zone. But for other shopping mall, we hired a drone flyer, and then this guy is making an image from his drone every 6 days. So we are collecting ground truth wherever we can. Also, oh yeah, exciting. In Singapore, you know Johor Way? Johor Way, the bridge that connects Singapore and Malaysia, Johor Bahru. And at EOS, Cheryl Tay, she found a CCTV data that is looking at Johor Way, and then she downloaded the scenes that is the closest to the Sentinel-1 SAR data acquisition, and she did the analysis comparing the scenes that show the cars and then the reduction of number of cars, and she did even inversion to estimate each size of vehicles, how much of a contribution each type of vehicle is having on the observed coherence. So we can do all sorts exciting stuff only if we have useful ground truth data.
Thank you very much.
So next we'll be taking the question from Park Hu-Ying. Park, can you unmute yourself and ask your question?
Hello, I would like to thank you for your lecture. I think it's very informative. So I have two questions. And just now you spoke about using drones for monitoring, right? So I would like to ask a similar question. So regarding UAVs for disaster management, response, and monitoring. So we know that one of the benefits of using UAVs over satellite imagery is low latency. It is on demand, and the images are of high resolution. So I was thinking if there is a trend towards using UAVs as opposed to satellite images. And so my second question is with regards to other disaster response, have JPL considered monitoring disasters such as oil spill, and like such oil spill events also require pretty fast responses regarding to oil spill cleanups and such. There are several proven methods such as using optical sensors, using microwave, using NIR reflectance. So I was asking, and there's a lot of challenges with respect to each of these techniques also. So I was thinking whether you have any suggestion, if there's any sort of frontier developments on such areas. Thank you.
Sorry, but you must be standing in a windy area or something. There was some wind noise.
Oh,
So
it was.
second question wasn't.
Oh, sorry, that's my
Second
bad.
question wasn't very clear. Is JPL monitoring something?
Oil spills. Yeah, I was asking with regards to oil spills as a form of
Oil field?
oil spills.
Oil spills. Oil
Yeah.
spills. Yeah.
Yeah, oil spills.
Yeah.
Yeah.
Oil spills, yes.
Yeah, so there
okay.
are.
Yeah.
Yeah.
Yes, I will address the second question first then. Yes, oil
Okay.
field, yes. Oil spills, yes. There are oil spills, and then JPL, there are efforts to map oil spill extent. They flew UAV SAR. So here's a UAV connecting to your first question. UAV SAR, it's a SAR system designed to be mounted on to UAV, Global Hawk, but it's not mounted on the Global Hawk yet. It's currently mounted on Gulfstream 3. It's a piloted airplane, but we call it UAV SAR. And we flew UAV SAR to produce the image of oil spills. And there are projects that for oil spill mapping, Kathleen Jones at JPL was doing that. And they deployed UAV SAR in Norway. In Norway, they have planned oil spill. They spill oil on purpose for this application. How well oil spill mapping can be done. And I know UAV SAR was deployed to image that planned controlled experiment of oil spilling. And for your question of drone being on demand, is that a good option? Or UAV is a good option? That is true. Like any aircraft, including drone or big aircraft, it's on demand, so you can always dispatch and fly. The complication is it takes logistics. Let's say there's an earthquake and you want to fly UAV SAR. And you have to get approval, you have to secure pilots, and you have to go through some paperwork in order to fly the plane. Also, that plane is usually doing something else because it has scientific mission. Sometimes it's flying somewhere in Iceland, sometimes it's flying in Brazil, in Japan. So it's not always available and ready. It's not standing by for disaster response. If there's a dedicated aircraft, yes, you can do it. But there's another thing. If I haven't shown, Hurricane Maria, for example, if there's a tropical cyclone induced damage mapping or flood mapping, there's still strong wind. And when the flooding is happening, there's still tropical cyclone lingering. For example, Hurricane Harvey, it takes almost a week to give way for other optical sensors or aircraft to fly. So back then, the satellite SAR data was the only hope at the early stage of this hurricane response. So so they are on demand and it's handy, but satellite usually, at least until now, and I think it's going to be more so in the future. Satellite's going to be the one that would fly and access the area first, safely. But drone is also has its own benefit, and it's very attractive. But there are pros and cons. It's an interesting question.
Any other question from the audience? If no, let's once again thank Dr. Yun for taking his time off amid his busy schedule to join us today in this webinar. And thank you all for your wonderful participation in this event. Before you leave this webinar, do scan the QR code for the survey or attendance form. We value your feedback to help us improve future webinars. Meanwhile, stay well and stay healthy.
Thank you.
Uh,
Thank you, everyone.
Thank you.